Is it? Okay, now it's working. So sorry. So I'm not sure if I have to repeat it. I'm not sure. Yeah, I guess you heard me. So I was so maybe again. So if you multiply out these products here, matrix times vector, and again matrix vector with these matrices that we know, then you arrive at these two equations. And what you see is a system of coupled equations, because you have what do you have? This is a differential equation in omega. These are two first order differential equations in omega and v, right? But you see that we have these full coupling here, because we have omega dot, omega v dot, and here the same. So we are fully coupled equations. Okay, maybe to better understand, let's look at the special case when we have the center of mass frame, the body fixed frame at the center of mass. If you put our body fixed frame at the center of mass, then it simplifies like this. Now, let's have maybe look at the first equation. And I was saying I would claim that this is actually the momentum balance. I mean, the linear momentum balance. Maybe would you agree on this? Or so what was the linear momentum? So how did we define the linear momentum? Exactly, you exactly know it. Oops. So the linear momentum was defined m times v. Pretty simple. And it's good that we talked about this actually. What if I and in the space fixed frame, for example, right? The Newton-Euler equation, I mean the linear momentum balance, the Newton equation, would be that this p dot is equal to the applied force expressed in the space fixed frame. And that would be it, because then that would be simply, m v dot is equal to f0. So this is the case when we would have expressed everything in the space fixed frame. Now we are not in the space fixed frame; we are in the body fixed frame. And now what we concluded, if we transform the time derivative in the body fixed frame, it looks different, because then, if now b is the frame in which we're expressing it, then this time derivative becomes p dot plus omega cos and everything in the b frame cos p. This would be that p. This would be the time derivative in the body fixed frame. This is what we arrived at the last lecture. Now we take this times m and f in the body fixed frame, right? Because this is the space fixed version, and that would be the body fixed version. So, and that's exactly what you see here. Because no, sorry. The m, of course, is already included in p. So yeah, and so this is the body fixed version of the time derivative of the momentum. And then, of course, if you say p is equal to m times v, I mean, m is constant, supposedly, if you're not working with rockets or things that burn fuel or something. Then, of course, this is just m times v dot plus omega cos m times v, right? You can take m out, and you get exactly this equation that we have here. This is exactly that equation, okay? Yeah, and the same applies actually to this, to the second form, because what we have here is the same. This, what we derive with this expression for the derivative in a moving frame applies to a general vector, because what we did it in fact for some vector a, some vector, right? Any vector, which means that, well, I can actually plug in for example, the linear momentum, the angular momentum, I can say like this, right? Omega tilde L is equal to, but in this case, it's the force. Okay, now we call the momentum. Sorry, the moment. I'm getting tired. And for some reason, we call it T. Okay, this is the moment. And yes, and so now, what is L? We said L is, of course, theta in the body frame, omega in the body frame, and then we are there because you can take this out, of course. I mean, you can say this is theta, and theta in the body frame is fixed, right? This is the big advantage. So essentially what we have is the time derivative of this plus omega tilde theta and all in the body frame. L, what is a bit strange now? Anyway, is equal to T in the B frame. And this is, of course, exactly the equation that you have here. So this one. So if you have a dynamics course, that is, if you have a good dynamics course, that is what you learn in the in the course, right? Where theta is the theta is the the inertia tensor. So now I was actually using B, right? But I was actually so I used B, but I should have used C because these equations only apply when we have when we have the theta and C, when we have, this is what we say here, that we have the frame attached at the center of mass. So this should be B. Otherwise, it's not correct because otherwise you get additional terms. Maybe look, I don't know which one. Look at, for some reason they are swapped. Okay, so this one would become, or let's say this one, that one would become this one, right? So the most general form is of the linear momentum equation is this one, right? Which simplifies to that one if you use the COM frame, center of mass frame. Otherwise, we have this. And what's the additional term? The extra term is, if you look here, I mean, this is the same, just by saying this is the body fixed frame. What comes on top of this is this here. And there's a nice way of explaining this, which maybe we shouldn't try to do. But maybe this one is interesting. Anyway, so what is D? What was D? Remember that we had in our mass matrix, we had this DBC vector. And the DBC vector was the vector from the center of mass to the frame we're using. Now, if this is, so, no, right. But if if C is B, then of course this is 0, and then the whole thing simplifies. That's why if this becomes 0, then we get, well, what's not? If this becomes 0, then we get here. And if this becomes 0, we get here. Okay. Yes. You could also try to understand this term here, because I mean, it's always the same argument, right? Because this term you see here, essentially, this is, again, this must be the same like this. Well, it is the same like this. And what is it? It is the, it's the time. I mean, this is the Coriolis term, right? This is a convective term. But this was essentially it's the same here. What I was saying is that this is the time derivative of the velocity expressed in the body fixed frame. Now, when we use the center of mass frame. But anyway, this time derivative business, that applies to any frame. So essentially, this is, again, the time derivative of the velocity of the body fixed frame expressed in the body fixed frame. And this is the additional term. Because what you see here is that, because what you see there is a very simple consequence of the fact when you have a rigid body, right, and you have a center of mass somewhere, right, and if it's free floating in space, about which point is it actually rotating? It's always rotating about the center of mass, right? And that means that if you are not sitting at the center of mass, I mean, if our frame is not, if this is FB, is not at the center of mass, then of course the linear velocity that we have to use is the one of the center of mass, plus of course an extra term. And this extra term is the one that, of course, this was the vector from the center of mass to dBc, we call it, right? So it's the other way around from dBc. Anyway, dBc that goes from the frame to the center of mass. Okay? So this goes from the center of mass, and then what we are using is, I mean, this is what we find in this equation here, is the velocity actually of this point, because this is what goes into there, and then you have the velocity of this point, and this generates again a kind of an offset angular momentum, and that's why we have it. We have it here. So this is a kind of an easy explanation for this.
But when we are using two frame, one is a centric mass and one is body fixed frame, would it be redundant or unnecessary?
We only use one frame. Yeah, I mean, essentially, I mean, eventually you use one frame. So you fix one frame somewhere, and then you have the equations of motion. So you have these dynamic equations here. Okay. The only thing is what parameters go into the equations, and what goes into the equations is, of course, a mass matrix. And now the big thing is, the only question is, how do you get this mass matrix here? And so you have to compute it somehow, right? And what goes into it is the information about the inertia and the mass relative to the mass, to the body fixed frame. I mean, to the one frame that you're using. Okay, but the one frame that you're using is not not necessarily at the center of mass. And you have to know the distance displacement to the center of mass, because otherwise you cannot do any computation. So it's not redundant in the sense that we have two frames. It's just that when you're not sitting at the center of mass frame, you need to know how the displacement from the center of mass. That's the only thing you need. Okay, yeah, so that's for this part. Any questions so far? Okay, then I would really briefly go into floating-based systems. I mean, I know this is already a lot, and now going to floating-based systems makes it even more challenging. But, no, I'm not going. Now we go to the motion equations first. Sorry, I didn't read it. So, okay, this was this one single body, right? Because now what we're having is one single body. But now we're looking, of course, we're looking at robots, right? That consist of many bodies, okay? And now we would like to have the motion equations for, I mean, the dynamic equations for the general systems, for kinematic chains. And that goes via the principle of virtual power. I mean, there are different ways. I mean, I'm not sure if what you heard in your mechanics course or any other course, there's this principle of virtual work, right? Have you heard about the principle of virtual power? Okay, no, okay, so you know the principle of virtual work. The only difference is, so what's the principle of virtual work?
Imaginary change in length or
Hmm.
imaginary displacement, small displacement.
Like a virtual small displacement, yeah, yeah, yeah. And the same goes with this, with the virtual power. The only thing is that we're not having virtual displacements. I mean, not virtual displacements, but virtual variations of the velocity. So yeah, that's it's more handy, because if you would use the principle of virtual work, then you would, as you say, need the virtual displacement. And the virtual yeah, it's not easy to say. It has to do with the use of coordinates. Anyway, believe me, this is just better. So what is the power, so to say? What is the total power of our system? But the total power of our system is just, I mean, you have, where do we say this? No, we don't. So we have n bodies in our system, okay? So now yeah, I mean, As before, we have a kinematic chain, and we have n links, and they are connected by n joints. And that's, I guess, okay. And the total power of this system, consisting of these n bodies, is of course, well, what do? You just look at the. So this is the wrench. I mean, this is the dynamic wrench, so to say. What the system is, what one body is generating. Then you add up all these wrenches, but you have to include some other wrenches, because maybe you should write this on a blackboard. Because when you have a system of rigid bodies that are connected, and they are somewhat geometrically connected, right? So if they are connected, so let's say we have our bodies, right? Let's say we have one, and let's say we have two, and they are connected by some joint. Make it simple. Let's say this is a revolute joint or whatever. So body one, body two. Okay. So each of them, I mean, the dynamic equation of them, let's say mi vi dot minus at vi transposed mi vi is equal to some wrenches we set, right? Some applied wrenches. Okay, I don't know. Let's say call them W app. Some wrenches that act on it from outside, gravity or whatever. Okay, now say, so this is maybe body I. Now we have I minus 1. And this is of course goes the same, right? I mean, maybe I don't have to write it, but let's do it. So I minus 1 transposed mi minus 1 vi minus 1 is equal to wi minus 1 applied wrench. Okay. Now they are connected. So this would be when you have a free floating body. So this one is free floating, this one is free floating, but they are connected. And they are connected because of the joint. So what kind of magic force is it that keeps them together? A constraint force. Right? We talked about this in the very beginning, when we said, for example, the revolute joint imposes 5 constraints. Right? Now to each of the constraints corresponds a constraint force. I mean a constraint wrench, because you have forces and torques that somehow keep them together. So they must be included in the balance equation, right? And let's call them WIC for constraint wrench. And this is the one that you actually can say, I could actually make a free body diagram, okay? So when you make a free body diagram, so you have one body, you have another body, as we did, and then you have these these magic forces that keep them together, because you would have a force here, and there's a force balance, of course, right? And maybe even a torque. I don't know how you make torques like this, and that goes into this wi. What is this now? But c, and wi, goodness, minus 1c. Okay, and they're somehow related, of course. Now, what is this principle of virtual power, or the principle of virtual work, saying? Why do you need it actually? What's the purpose of using the? I mean, this is always something puzzling to students. I mean, we have the equations already. Why do I need another principle of virtual work, virtual power, whatever? Because what it says is that essentially there is this D'Alembert principle. It says the work or the power performed by constraint forces is zero. In a sense that, or the other way of saying, constraint forces do not perform any work. What does it mean? It means essentially, for example, if you have a revolute joint here, right? So if you have a revolute joint, there could be a torque here, right? But there's certainly, I mean, let's say there's a torque, whatever. You can have a torque. So, and then they would move somehow. But whatever you do not feel in your equations of motion, and also otherwise, the constraint wrench, which is the one that keeps this all together, right? So this WC is somehow acting in quote unquote orthogonal to the free motion, right? So this is just the magic force that keeps all together. Okay? But you don't feel it because how to say, I mean, the door doesn't feel the constraint force in the hinge. When you open the door, you don't feel that there's a big force actually holding the door. No, for the free motion, you don't feel this. And the same is with your body joints. I mean, you don't feel the force that is acting in your knee, for example. You feel the torque because this is what you have to generate, but you don't feel the force unless you have an overload. And this is it. And this is the reason for using, yeah. But this statement is often incompletely stated. Because what it says is that constraint forces perform no work, and this sentence goes on actually, for admissible motions. Okay, what does it mean for admissible motions? Because this is the important point. Now I have these wrenches here, these constraint wrenches. So I have them in my equation, okay? But essentially I don't need them. I would to get rid of them, right? Because they should not appear according to this statement in my equations. So, and that's the point. And now I lost what I was about to say. What will I say? No, I lost what I want to say. So I'm getting tired. Yeah. Oh yeah, for admissible motions, that was what I want to say. So what are admissible motions for this? So which motion is permitted by the revolute joint? And that's clear, it's a revolution. Yeah, clear, right? So for any other, and only for those, no. So for these motions, when the two bodies perform a rotation according to the rotation joint, the virtual work is zero. The constraint forces perform no work on the system. Okay. In other way, saying if I would like, I mean, I'm virtually, and this is the idea now. If virtually I do something which is not admitted, like bending it so that not doing rotations, but rotation but an axis which is not the rotation axis, then I will feel them. That makes sense because then you feel it, right? If you push, if you go to the door hinge and you push it, then you will feel a force, but not in a free direction. And that's the important thing. And this is what comes in here because these twists in our case, they must be admissible because what it says here, this is the power again. I mean, this is now so this for each of the bodies. I mean, this would be for all bodies. This is the equations that we got, the Newton-Euler equations. Now the statement is that if I take the power performed by these equations by these bodies, and the power is again, of course, the velocity times this wrench, the total sum of wrenches. That should be zero for admissible variations of the velocity. And now the question is, how do we get actually admissible variations of the velocity? So how do I know what velocity of body I mean of all the bodies, is possible, is allowed according to the kinematics? So how do I know that this body I can do only rotations relative to the predecessor, body I minus 1? How do we know this? Well, we know already because we have already modeled the kinematics, right? So I know exactly how to express the admissible, that means possible, velocity of body I, and hence the virtual variation of it, because we have the Jacobian. The Jacobian of body I times q dot gives you the velocity, I mean the twist of the body. And by definition, this is the twist that is possible, right? And it's as it is. I mean, it's according to the open kinematic chain, it does what it's allowed to do. And that's it actually, because then we are there, because then we have this, of course, for all the bodies. We can plug this into the big, system twist, big V, and also the system Jacobian. And then we could actually do this, because replacing this part, the delta Vi, the variation of the velocity Vi, by this equation, we get exactly this. We would have the sum of Ji times this equation plus Ji minus 1 plus this equation I minus 1, which is essentially saying the same like you can take this, the transpose of J, because the big system Jacobian was the first Jacobian, J1, J2, J3, and so on. And if you transpose it, you get actually, what you get here is, this is J1, J2, J2, 3, 4, up to n. And in the end, what you get, because this is essentially lining up the equations. I mean, in this matrix, we are lining up the equations of the n bodies. So essentially, I'm just writing down the equations. And what you and then multiply it here, what you get is exactly this. So you multiply this equation with J1. It's like a scalar product, okay? And then the second one with J2 and so on. And that is essentially the same as this here. And what I already imposed here, or used, so to say, it's not imposed, it's a fact, is that the constrained wrenches do not perform any work or any power. Which means that if you look at the term that is missing, it's the delta Vi transposed times Wi constraint, because that is actually the power due to the constrained wrenches. And the power due to the constrained wrenches performed by admissible velocities is 0. So this term is actually already cancelled. I mean, this becomes 0. That's why it doesn't appear anymore. Okay, and then we almost have the final equations of our, the dynamic equation for our system. Because, okay, this is the one that we got. Okay, and we know that, so what do we have now? How many equations do we have? I mean, look at these equations. How many equations do we have? Yes, we have n equations, because J transposed is an n times 6n matrix. This is a 6n vector. No, it's not true. Yeah, 6n vector. So we get n equations. But for how many unknowns? Well, the unknowns are still the velocity 1 to n, which means 6n unknowns, because each of them is 6. So we have n equations for 6n unknowns. That's somehow not nice. And that's why we need more equations. So we know more than we know, or maybe before we go here, how many unknowns do we have here? We said 6n. That's not the full story, because we have the 6n, the n twists, which makes altogether 6n independent. But what else do we have? I mean, remember that all the m's, everything depends on Q, on the force of the system. And that's what you see also when you say, okay, we can replace the velocities by our Jacobians, right? So you would replace each the velocities by the Jacobian. And in this way, you could actually, you could stick with this equation. So you would have n plus 6n equations for the n unknown q, and for the 6n unknown v1, vn. So we have 7n equations. You could do that. Sometimes people do this. The benefit could be that you have a first order equation, because you have a first order differential equation, right? Everything appears here with the first derivative, time derivative. But that is not the normal kind of approach, okay? Yeah, good. Because what you certainly can do is, okay, this is maybe just a bit more detail. Yeah. Yeah. Before we proceed, maybe we should try to write it in a different form. Okay, so this is okay. Let's say this is what we arrived at. But you could actually write each of these. I mean, these equations here, all of these equations, we could write them in a different way. And let's say that we introduce a matrix and these diagonal matrix, because what you could do is you introduce this big matrix M, this let's call it B, and a big vector W. What I can do with this is very simple. I mean, if you write it out, it's essentially the same as this one. If you say M times V dot, right, what you get is, so M times V dot, so V is the vector with all the V's in there, the system twist, is essentially this first term. No, I mean, yeah, is the first term. So M times V dot is just M, this dot, to get a vector, which is this part. If you say minus B transposed MV, so this one, B transposed MV, it's essentially this one. It's this transposed, and that transposed times M1, and so on, times V. So this part, I mean, forget about the G transpose for the time being. So this part is essentially this one, okay? Well, and then you bring maybe this on the right-hand side, just not to have 0, but you have the W, and the W goes into here, okay? And then you have to pre-multiply everything with J transposed. So essentially, with using these matrices, we have the same, we have expressed that equation system. And what this is helping us, and how this is helping us, is simply, okay, first of all, you can write it in a different way, and so on and so on. But what is more interesting is to get a final form for this. And maybe just go briefly, because in the end, it's going to be pretty simple. So let's say we start with here, and we introduce this equation for the kinematics. So this is what we found from the principle of virtual power. Okay. Now I introduced this equation for V in here, and for V dot, this was the one that we had in here. Where you just plug it in, this one goes in here, you get this term, and then you get this term, minus this here with M multiplied with V, which is this guy here, and that's it. Okay, the only thing which I don't like is J dot, because I would like to have an explicit form for J dot. And remember, we have the explicit form for J dot. That was the one, it was minus capital A, little a times J. Okay, that's what we had. And these matrices are very simple. You saw them. Okay, now introducing this in here, J dot equal to this, you get minus, AA, and that's it. So, very nice. Of course, you can factor out the Q dot, and in the end, what you get is this matrix, and this matrix times Q dot. And this is almost the end, because what is this? Yeah, there's a different version of doing it. Yeah, that's not important. So, and by using this to get actually this expression, because what you can say is that, okay, maybe go back. So this, of course, appears as what we call a generalized mass matrix. I mean, first of all, M had so the dimension of M was 6n, 6n, right? So M had just all the mass matrices on the diagonal. So each of them is a 6, 6 matrix. So we have n of them. It's a 6n, 6n matrix, okay? So, and then what we get here is, of course, so J transposed is n times 6n, right? So we get here, and J is 6n, n. So altogether it gives you an n matrix. Okay, and the same goes here. This is also an n, I mean, the whole thing is an n times n matrix. And the naming goes like, this is called the generalized mass matrix, right? And if you have this in Lagrange mechanics, if you have maybe had your course in Lagrange mechanics, then you have maybe heard about it. M is the generalized mass matrix, Q are the generalized coordinates. I mean, typically the joint coordinates, right? And in robotics, when you work on robotic manipulators, this is the the joint space inertia matrix, sometimes called, and that's the joint accelerations, of course. And then this term, I mean, the remaining thing is, and now C is correct. It's usually called like generalized Coriolis matrix, centrifugal Coriolis terms. And they are, so these are I mean, this expression here is a term that is quadratic in the generalized velocities. When I say it's quadratic in the generalized velocities, that is because let's look at what happens. How does this C depend on Q dot? So it depends on Q dot by looking at the dependencies. Okay, so this, let's say, look at this one, capital A, little a, okay? So A depends on Q, that's fine. But this little a matrix depends on Q dot. And it depends linearly on Q dot, right? Because it just depends linear. I mean, it's just, each of this factor is multiplied with Q dot. So, and the same goes with B, because B, we had it somewhere before. B was somewhere. B. I don't know where we had B. Where we had B? I think we had it before somewhere. At the other lecture, maybe. Yeah, could be. There we go. Okay, there we go. So I have it summarized here. Oh yeah, I should have just pressed one button more. Yeah, so what I was saying is that A depends linearly on Q dot. The rest does not depend on Q dot. B depends also linearly on Q dot because it depends on V, and V depends linearly on Q dot, right? So this term, I mean, the C depends linearly on Q dot. If you multiply this with Q dot, so the whole thing is quadratic in Q dot. And this is always important to mention because this is why we have this generalized, this Coriolis matrix or centrifugal matrix, because Coriolis and centrifugal terms, they're always forces depending quadratically on your velocity, right? Whenever you have something spinning and you have a Coriolis or centrifugal force, it is quadratic in the velocity. And otherwise, I mean, as an engineer, you could also go and check the units, right? If the units fit. And if this would not be quadratic, then the units wouldn't fit. Yeah, anyway. So this is essentially the recipe for constructing the dynamic motion equations in a very, I would claim, compact and efficient form. Because what do you need? You need matrices. You have this capital M, right? So in this matrix is constructed from the body fixed. I skipped this B. So the body fixed mass matrices, they are constant. I mean, so the mass matrices is what you have to find anyway. So you go to your cat, for example, if you have a cat drawing or a cat model or whatever you have to find the mass, of course, and you have to find the center of mass, and you have to find the inertia tensor, the inertia, the moments of inertia. So this is what you have to do no matter how you do the dynamics, okay? So then you have to have these matrices here, the B matrix. So what you do is you evaluate these equations for a given state. When I say a given state, what is a state? A state is always the position and velocity together, right? It's called the state space also. The state space is the space of Q and Q dot, or let's say the position and the velocity. That's the state of the system. Now, in a given state, you evaluate these equations, right? What I'm saying is that you evaluate the equations for given Q and Q dot, not for Q double dot. Maybe you do, but usually we don't. Depends. So why I'm saying this. So given is q and q dot. You can compute the velocities by using the forward kinematics, which is essentially, that thing here. So this is what you had from your kinematics. From the robot kinematics, you get from the joint velocities, the q dots, you get the v's. And then you plug this in this very simple matrix with these tilde matrices. And then you have again you have q dot, you have it, and then you plug it in here. So you have again this constant matrix, because these coordinate vectors are just constant simple vectors. And you construct the matrix, this 6 times 6 matrix that we had this morning, and then you have this matrix. Then you make this J, which is equal to AX, and the A matrix is just the these adjoint, this triangular matrix here, with the adjoints of the transformation matrix, the relative transformation matrices from 1 to 2, 1 to 3, and so on. And then you have the equations. Then you're essentially there, and you have the full set of equations, and you can blindly implement them. I mean, you don't necessarily have to understand what it all means. You just take it, implement it, and it should work. Okay. And the steps are: first implement kinematics, which means this part. And then do those equations, then you have it. For a given state, you can possibly, and what we have here is a second order differential equation. It's a second order ordinary differential equation system of n ordinary second order differential equations in terms of q. So you can solve this, and then you get the motion of your system. And that is easy said, but not easy done. Because, so when I'm saying solving them, there are two, do we have it here? No. There are two applications actually for this. One is the forward dynamics, and one is the inverse dynamics. So the forward dynamics means given q, I didn't maybe say what q is. So q are the so-called generalized forces, right? That might look very complicated with all this, but essentially what it is, it's the joint torques, right? So must be, because if these are the joint angles, then that must be the joint torques. So sometimes you call it tau, I guess, or so. And this is just your driving torque in your revolute joints, for example, right? So and if you want to know the motion of your system when you apply some torques, you have to start from a given state, so you know where your system. I mean, you know the state of your system at the moment, and then you apply a torque, and then you get, by solving this equation, you get the motion, which means you get q as a function of t, because the unknown is q double dot, and this is what you're solving for, right? I mean, for q of t. So and so on. And maybe this is again a summary. Summary. I did it again. These are the things you need. Yeah. Okay. There's gravity, miss. Yeah. So maybe one important element here of these generalized forces, which are the torques in the end, is of course the effect of gravity. The effect of gravity is very simply implemented. So what is gravity? Gravity is a funny thing. It's an acceleration without having a motion corresponding to it, right? So the body is always accelerating. I mean, the Earth is so to say accelerating this body without actually moving. And this is the vector of gravity. It depends a bit on the sign convention, up and down, up and down. Let's say we have minus g, and then how do you get and this is a wrench, by the way, right? So this is supposed to be a wrench in the sense that we have a moment and a force. This is an acceleration. Sorry. We have a linear acceleration and an angular acceleration and a linear acceleration, right? So the linear acceleration, and we have homogeneous. This assumption, this version is true for the assumption that we have a homogeneous gravity field, which means that we have no torque, which means no angular acceleration. When would we have an angular acceleration? Because everything is just accelerated linearly. When would you have also like an angular acceleration? But this is if the gravity would not be homogeneous. Because the assumption is that at any point here, we always have the same acceleration, which, to be precise, is not correct, right? Because you know the Earth is some sort of a ball and so on, and so it's always like this, but it's very big, so in the end, it's okay. Yeah, so, and you transform this gravity wrench, this acceleration wrench, backward to body I, because h 0I, which is 0 is missing here, I mean omitted. The inverse goes from the space fixed to the body I. Then you have, so this term actually gives you the acceleration in the body fixed frame. And then you multiply it with, I mean, this gives you an acceleration, and you multiply the acceleration with the mass, and then you get the corresponding static wrench out of it. And this is what you have to include if you have gravity that goes on the right hand side. No, anyway, it goes on the left hand side if you have the minus there. Because this, of course, is for body I, and you have to do this for all the bodies because the gravity acts on all the bodies. So this is what you have to do, of course, for I equal to 1 from 1 to m. And then you can do this by using, again, the big matrix M, and by using this matrix, because you just sum them up in the vector, and then this formula is giving you the complete gravity for all the bodies. So essentially what you have here is the Wi, W1 to up Wn. Okay, I guess this is so good so far. Maybe we should elaborate a bit for the last minute on the use of these equations. So be honest, have you seen them before? Yes. Next honest question, have you used them before? For what? For manipulator, correct. But what did you do with the equations? To calculate torque. All right. Because this is actually the opposite what I mentioned. Anyway, Lagrangian mechanics, but you got those kind of equations, right? And then you use the equations to compute the torque, you said. Huh? To compute the acceleration. Because there are two applications for this. I'm not sure. Do we have time still? Yeah. Yeah. I just want to finish this with a little discussion. Okay. So you have these equations in whatever form you have them, right? So, and now you have different, okay, because you use, I understand you use tau, then let's use tau. So these are the joint torques, for example. So there are two uses of these equations, and you said you computed the acceleration out of this. For what purpose? Yeah, I mean, what you could do is you could solve this for the acceleration, right? So, and how do you do this? You say this is equal to the inverse of m. And then you have tau minus c times q dot, okay? And this is what you could use for integrating the motion equations, for example, right? Because there are numerical integration schemes for such explicit differential equation. So you plug this into the equation, into the computation scheme, and it solves for a given tau, you get the q of t. In robotics, very often we are interested in the inverse problem, which is called the inverse dynamics, in a sense that I give you a motion, I give you q of t, which is the one I would like to achieve. So I would like to have my system performing according to q of t. So for example, for a robot, I say the joint has to move like this and this and that. because you did some path planning and so on. And I would like to know, because if you have this, you also have a Q dot, and you also have Q double dot. If you know Q of theta, you know everything. And out of this, I would like to know the torques that I need to actuate my system so that it actually performs the motion that I want. And that's easier. I mean, much easier than solving the equations. Because what you have to do is you just take this, plug it in here, and then you have it, right? You just have to evaluate your motion equations for the given, Q of t, for the given, trajectory and velocity and acceleration of your system that you want to have. And this is called model-based feed-forward control, right? So when you have a model for your robot, then you use this, if you have correct model, of course, as a feed-forward for your system, and then you do a feedback loop with the PID or whatever you want, right? That's a very simple way of doing it. But this is an important step actually for the nonlinear model-based control of this kind of systems. And I understand we are out of time, so we have to stop.